Hey guys, so the last time we were here, we went over how to calculate the percent composition of a compound. There's two scenarios that we went over. The first scenario was if you're given the masses of each of the element in the compound and you're already given the amount of the mass of the total compound. So that one's pretty easy because again, all you have to do is for each individual element, you need to put the given mass of that element over the mass of the compound times 100%, which should give you a percentage of that element in that compound. And you do it for all the other elements that are in that compound. And the last thing that we went over, again, is calculating percent composition if you're only given a formula. So this is the last thing that you've seen. This was the exit ticket that you guys were working on last Wednesday, I believe. All right. So you had two things that you need to find the percent composition for. You have ethane and sodium hydrogen sulfate. Ethane, again, you know that the first step, if you're only given the chemical formula, is to find the molar mass of the compound. For you to do that, you need to find the mass of each element, then look at how many atoms you actually have of that element in that compound. So if we're looking at ethane, the formula is C2H6. That means you have 2 carbons and 6 hydrogen. So if you look at the periodic table, you know that carbon weighs 12.0 grams because we're rounding everything to the nearest tenth, even before you add everything up. So you know that carbon is 12.0 grams. You have 2 of them, so you know that that is total. 2 carbons is 24.0 grams. Then you have to look at hydrogen. You know that hydrogen's mass is 1.0 grams each. You have 6, so total, you know you have 6 grams of hydrogen there. So total with the carbon and the hydrogen, 24 grams for the carbon, 6 for the hydrogen. You know that the total mass is 30.0 grams of ethane. Now to find the percent composition of each compound, you know that, well, if I have 24.0 grams of carbon and I divide that to 30.0 grams of the whole compound, then you multiply 100%, then you get the percent composition of carbon, which is in this case about 80.0%. Since you only have 2, if one is 80%, then you know that the other one will have to be 20%. So the percent composition of carbon is 80% and the percent composition of the hydrogen is 20%. Letter B, you have sodium hydrogen sulfate, which is NaHSO4. So in this case, you have 4 different types of elements. So that means that finding the molar mass would be a little bit more work. So you need to look for sodium in the periodic table. Right? Once you do that, you know that sodium is about 23.0 grams. Since there's only one, you have 23.0 grams there. 1 hydrogen, which is at 1.0 grams. Then you have sulfur. Sulfur is at 32.1 grams, right? And you have oxygen, which is 16, but you have 4 of them. So 16 times 4 gives you 64.0 grams. So again, sodium, which is at 23.0 plus 1 plus sulfur, which is 32.1 plus 64, you know that the molar mass of that sodium hydrogen sulfate then would have to be 120.1 grams. So now you have to individually find the percent composition. So sodium would have to be 23.0 divided by 120.1 grams. You should get 19.2% of sodium. Then for the hydrogen, you go 1 divided by 120.1 grams times 100 to give it a percentage. It would be 0.8% hydrogen. Then you have your sulfur, which is at 32.1 divided by 120.1 should give you, or times 100 gives you 26.7% sulfur. And lastly, the oxygen, which you have 64 grams of. So 64.0 grams divided by 120.1 grams times 100 gives you 53.3% oxygen. So again, this should be the final answer for the exit ticket that you guys did the last time we were here. So now we're going to move on to a new concept, which is all about using percent composition as a conversion factor. You know that a conversion factor must be equivalent. It must be equal to 1. They might have different units, but they should be equal. So we're going to use some of the information that we will be seeing and use that as a percent composition, as a conversion factor, so that we can solve for whatever they're asking for. So it says right here, you can use a percent composition to calculate the numbers of grams of any element in a specific mass of a compound. To do that, you need to multiply the mass of the compound by the conversion factor based on the percent composition of the element in the compound, which is again equivalent to 1. What I mean by that, that's kind of weird, right? It's wordy, but here you go. So suppose you want to know how much carbon and hydrogen are contained in 82.0 grams of propane. Again, they didn't even give you the formula yet, but at the bottom you know that propane is C3H8 and you have 82 grams of that. You already know that propane is 81.8% carbon and 18% hydrogen. So that means that if you have 100 grams of propane, then 81.8% of 100 is what? 81.8 grams, right? And 18% of propane would have to be, or 18% of 100 grams of propane will have to be 18 grams, right? So this is pretty much letting you assume that if you have 100 grams of a sample, then you can convert that percentage into an actual mass. You can use this, like what we said, to use as a conversion factor to use in your dimensional analysis. Again, if you have 82 grams of propane and then you're trying to find out the percent composition of carbon, right? So what this is pretty much saying is that, well, you're asking yourself, what is 81.8% of 82 grams? Right? And what is 18% of 82.0 grams? So that's the question, because they're asking you again, what is the percent composition of, or what is the mass of carbon and what is the mass of hydrogen in that 82.0 grams of propane that you have? So this is what this is literally saying. So if you have 82 grams of propane and you're trying to find the mass of carbon in that, you know that 81.8% of the propane compound is carbon. So for you to get rid of that percentage and turn it into grams, and you know that, well, if you have 100 grams of propane, then 81.8% of that is 81.8 grams. And that is where they got that conversion factor from. Same thing for the hydrogen. You know that 18% of the propane compound is hydrogen. So if you have 100 grams of propane, or 18% of that would be 18 grams. And that's where they've gotten that 18 grams up on top for the first conversion factor. So right now, you might be asking yourself, well, do I need that conversion factor? No, not necessarily, because you can do it simpler if you just ask yourself, what is 81.8% of 82? So instead of using that first conversion factor, which is 81.8 divided by 100, it's the same thing. If you just think of 81.8% and turn that into a decimal, you know that that's 0.818. So it's the same thing as multiplying 82.0 to 0.818. And you know that, well, that's going to give you the same thing, because when you do that equation, that's you pretty much answering what is 81.8% of 82.0 grams. Does that make sense? Nope. If not, you can ask Mr. Minez or the teacher that's supervising you right now. This is what the book is saying. But again, you don't have to follow this. You don't have to use it as a conversion factor. You can simply just find 81.8% of the 82.0 grams that you have, and what is 18.0% of the 82.0 grams that you have, and it should give you the same answer. So again, 67.1 grams is 81.8% of 82 grams, and 15 grams is 18% of that 82.0 grams. Let's put this out in a scenario. So Steven was cleaning out one of his airsoft gun when he saw that there's rust on one of his favorite aluminum airsoft handgun. As he was trying to buff out the rust, he started to think about this problem. How many grams of aluminum are in 25.0 grams of aluminum oxide? And they gave you the formula there, which is Al2O3. So all that you know is that you have 25.0 grams of aluminum oxide. You don't know anything else but that. The first thing that you need to do is find the percent composition of aluminum. Why just aluminum? Well, the question is asking how many grams of aluminum are in 25.0 grams of aluminum oxide. So you can go and find the percent composition of both aluminum and oxygen, but you don't necessarily have to, because all the question is asking for is for aluminum. So the first thing that you need to do is, just like the previous problem that we did, you need to find the percent composition of the aluminum in that aluminum oxide compound. So how do we do that? Well, you're not given any mass, so that means you need to look at your periodic table and find out the mass of the components that you have. So the first thing is, let's find the mass of aluminum. Each aluminum is 27.0 grams. So if you look at your periodic table, again, on the third group, you will find aluminum, and aluminum is, when rounded to the nearest tenth, is 27.0 grams. You have two of them, so you know that you have 54 grams of aluminum. And if I'm going to do above and beyond work, then I'm going to look for oxygen. Each oxygen is 16 grams. I have 3 of them. So total, I have 48 grams of oxygen. So this is what I've figured out so far. Again, aluminum is 27.0 grams. I have 2 of them. So I have 54 grams of aluminum. Oxygen, 16.0 grams each. I have 3 of them. So total, I have 48.0 grams. So the molar mass of Al2O3, or aluminum oxide, will have to be 102.0 grams. So now to find the percent composition, since I am only looking for aluminum, that's the only one that I really need to find. So I don't need to do the extra work, because if you read the question, they're only concerned about aluminum, or Steven is only concerned about aluminum. So I'm going to put the mass of my aluminum, which is 54, over the mass of the whole compound, which is 102.0 grams. I multiply that to 100 and I get 52.9% aluminum. So in that 102 grams of aluminum oxide, 52.9% of that is aluminum. So do I need to find the percent composition of oxygen? Not necessarily, because all I need is, like what I said, the aluminum. So if we're following the book way, I'm going to turn that 52.9% into grams, right, over 100, so I can use it as a conversion factor. So where do I get the 25 grams from? That is the starting mass that was given to you in the equation. So if we go back to the initial equation, we said right here that 25.0 grams of aluminum oxide is what you have. So going back to the equation, right, I'm starting with what I'm given, 25.0 grams. Then my first conversion, 52.9 grams over 100. Where did I get that 52.9 grams? Well, I know that 52.9% of the aluminum oxide is aluminum. So I'm using that as a conversion factor. Or like what I said, you can just go, what is 52.9% of 25.0 grams? When you do that, you should find that 13.2 grams is 52.9% of the 25 grams that you have. So since they're only asking about aluminum, then that is all that I need. So I'm going to give you guys a problem that you can work on with your partner. Make sure that you guys talk to each other and ask each other good questions. So here is the question. How many grams of iron are in 21.6 grams of iron 3 oxide? The formula is Fe2O3. So I will ask your teacher to pause the video real quick so that you guys can start. So the first thing that you should do is find the molar mass of your iron 3 oxide. So I'm going to look at the periodic table and look for the mass of iron. Again, iron is in the middle. Its atomic number is 26. Each iron is 55.9. 55.9, but I have 2 of them. So I know that 2 iron atoms is about 111.8. Then oxygen is 16.0 each. I have 3, so I know I have 48 total. So if I add up the 111.8 plus 48, I should get 159.8. So to find the percent composition, you go, well, I'm really only concerned about iron because that's the only thing that they're asking for. So I'm going to go and put the mass of the iron that I have, which I have 2. So it's going to be 111.8 divided by 159.8. You multiply that by 100, you get a percentage. So you go 111.8 divided by 159.8. You should get 69.96 or about 70.0%. So what is 70% of 159.8? Now that you know that about 70% of the iron 3 oxide compound is iron, you start with the mass that they've given you. So you know that you're starting with 21.6. So the question will be, what is 70% of 21.6? Because 70% is iron, and that's what they are concerned about. So you go 21.6 times 70 divided by 100 should give you about 15.1. Why 15.1? Well, you're only starting with 3 significant figures in 21.6. So your answer should also just be 3 significant figures. So your answer should be 15.1 grams of iron. So now we're going to move on to another concept, which is how to find the empirical formulas of the compound that you are working with. So let's start by defining empirical formula. What is an empirical formula? Well, it is the basic ratio that gives you the lowest whole number ratio of the atoms of the elements in that compound. So again, it is the basic ratio that gives you the lowest whole number ratio of the atoms of the element in the compound. The empirical formula of a compound shows the smallest whole number ratio of the atoms in a compound. So I want you guys to write down this definition. If it's too small up in the screen, you should have your books open into section 3, and you should be able to find the definition of empirical formula there. So here you go. So why is it important to find the empirical formula? Because we need the empirical formula to actually get the molecular formula. So this is a step-by-step concept. So we did the percent composition for a reason. You need the percent composition to find the empirical formula. You need the empirical formula to find the molecular formula. So how do we find out the empirical formula of a compound? So I'm going to do an example first, then I will let you guys do a problem so that you can apply what you are learning. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. It's asking you, what is the empirical formula of the compound? So again, when you're given a question, the first thing that you need to ask is, what is this question asking you for? So you know that this question is asking you for the empirical formula. The second thing that you need to do is write down everything that you're given. You're given that you have 25.9% nitrogen and 74.1% oxygen. So I will write that down, right? And this is what I know, and that is what I'm looking for. So I'm looking for the percent composition of nitrogen and oxygen compound. So the first thing that I'm going to do is literally take that 25.9% nitrogen and just turn that percent into grams. Why am I doing that? Well, I'm assuming that if you have 100 grams of the nitrogen oxide compound, then 25.9% of that is 25.9 grams. And I will do the same thing for the oxygen. I will turn that 74.1% of oxygen into 74.1 grams of oxygen. So as you can see, that's what I did there. 25.9 grams of nitrogen, 74.1 grams of oxygen. But I don't want grams. I'm looking for an empirical formula. In an empirical formula, you need moles. So how do I convert that grams into moles? Well, I'm going to look at my cheat sheet and look at the mole map that you have from mass to mole. You know that the first conversion should be 1 mole over the molar mass of what you're working with. So I'm working with nitrogen here, and a nitrogen weighs 14.0 grams, and that's where I've gotten that 14.0 grams in the first conversion. And oxygen is 16.0 grams. That's where I've gotten that 16.0 grams in the bottom there. So as you guys can see, the gram unit will cancel out. I'm left with the mole. All I have to do is do the math. So I'm going to go 25.9 times 1 divided by 14.0 grams. I will be left with 1.85 moles of nitrogen. I will do the same thing for oxygen. I will go 74.1 times 1 divided by 16.0, and I get 4.63. So the next step after I've converted that percent into grams and that grams into moles is I'm going to look at my two products. I have 1.85 here and 4.63 here. Do you guys see that? 4.63 and 1.85 right here. I'm going to pick the smallest mole that I have. Right? In this case, 1.85 is the smallest mole that I have, and I will divide both the products that I get by that mole. So what I mean by that, so again, I'm going to divide 1.85 moles of nitrogen to 1.85 because that's the smallest, and that will give me a whole number 1 mole of nitrogen. So if I do that for 4.63 divided by 1.85, I get 2.50 moles of oxygen. So in this case, when you have a formula, you know that you cannot have a non-whole number. Like this will not work. N 1.85, O 4.63 doesn't work. But so that's why we are dividing everything by the lowest mole that we've gotten first. But as you guys can see, it works for nitrogen because a number divided by itself will give you 1. But in this case, 4.63 divided by 1.85 gives you a non-whole number still. So that means that I need to do one more step so that both my moles will be a whole number. So what should I do? Well, the easiest thing to do would be to just look at it and say, well, if I multiply both my moles by a certain number, can I turn that into a whole number? Well, yeah. So if I look at 2.5, if I multiply that by 2, I know that I would get a whole number, which is 5, right? So that's what I'm going to do. So I'm going to go, well, whatever I do for one, I have to do to both. Since I multiplied 2.5 by 2, I need to multiply 1 mole of nitrogen by 2 also. So that means that I have 2 moles of nitrogen and 5 moles of oxygen. Good? Because again, we can't have that non-whole number down here. They all have to be a whole number. Again, lowest whole number ratio is what empirical formula tells you. So in this case, I have 2 moles of nitrogen and 5 moles of oxygen. So the formula will be N2O5. Does that make sense? Hopefully it does. So here's an example of a problem that you can do. Let's start with letter A. So I'll give you guys some time. I'll ask the teacher again to pause the video. Then if once everyone is done talking to your partner, again, help each other out, then the teacher will play the video again, and hopefully the results that I get is the same as the result that you've gotten. So pause real quick. Good? So the first thing that you should do is turn that percentage into a gram unit, because you can turn that gram unit into the mole unit that we do need for the empirical formula. So the first thing that you need to do is go 94.1% and turn that into grams. So it's going to turn into 94.1 grams of oxygen, and that 5.9% of hydrogen will now be 5.9 grams of hydrogen. The next step would be to turn that grams into mole. So that means that we need to find the mass of oxygen and the mass of hydrogen. The mass of oxygen in the periodic table, if we round it to the nearest tenth, is 16.0 grams. And the mass of hydrogen, if we round it to the nearest tenth, is 1.0 grams. So what I'm going to do is go 94.1 grams. Then my first conversion would be 1 mole of oxygen is about 16.0 grams, right? This would give me moles. I know that I have 5.88 moles of oxygen when I do this math. This gives me 5.88 moles of oxygen. Next, I'm going to go 5.9 grams of hydrogen times 1 mole of hydrogen, and the mass of hydrogen is 1.0 grams. And you know that 5.9 times 1 divided by 1 is the same thing. It's 5.9. So I have 5.9 moles of hydrogen. So again, I have 5.9 moles of hydrogen. So I'm going to look at the 2 moles that I have. I have 5.88 here and 5.9 here. The smallest one I have is 5.88. So I'm going to use that to divide the 2 moles that I have so that I can get at least one of them to be a whole number. So I'm going to go 5.88 divided by 5.88. That should give me 1. Then I have 5.9 divided by 5.88. When I do that, I get 1.003. So that is close enough. If you're 0.003 off to 1, then I would just round it to the nearest tenth and you get 1. So it's the same thing. So you have a 1-to-1 ratio. Empirical formula for that first one should be just OH. So it's literally almost a 1-to-1 ratio, because the number that you get when you divide 5.9 to 5.88 is 1.003. So instead of me multiplying both numbers by thousands, I'm just going to round that 1.003 to 1, and that gives me a 1-to-1 ratio. So again, it should give me the empirical formula of OH. So if you're working on B, you have 3 components here. You have mercury, sulfur, and oxygen. So you need to find the empirical formula of each compound. So that means that I need to turn that 67.6% of mercury into 67.6 grams of mercury, that 10.8% of sulfur into 10.8 grams of sulfur, and that 21.6% of oxygen into 21.6 grams of oxygen. So I'm going to start with mercury first and convert that 67.6 grams of mercury into moles of mercury. So I'm going to start with 67.6 grams. I need to find the mass of mercury. So if you're looking for mercury, you know that it is a transition metal, atomic number 80. So if you look at the mass, it's 200.6. 200.6, 1 mole of mercury. So when you do the math, you go 67.6 grams times 1 mole divided by 200.6. You get 0.337 because you have 3 significant figures. So 0.337. 0.337 moles of mercury. Now I'm going to deal with the sulfur. So I have 10.8 grams. I have 10.8 grams of sulfur. I need to find the mass of sulfur. So 1 mole of sulfur, the mass of that is 32.1 grams sulfur. So when I do the math, I'm going to go 10.8 divided by 32.1. I get 0.336. So again, I get 0.336 moles of sulfur. Good. So 0.336 moles of sulfur. Now, I have to deal with the last one, which is oxygen. Oxygen is 16 grams. So I'm going to go 21.6 grams of oxygen, 1 mole, 16.0 grams right here of oxygen. That should give me, if I do the math, 21.6 divided by 16 gives me 1.35 moles of oxygen. Again, I get 1.35 moles of oxygen. So I picked the least. Again, 0.337 and 0.336, that's close enough. So I go 0.337 divided by 0.336. I get 1.00297,619. But then again, like what I said, instead of me multiplying that to a gazillion numbers, I'm just going to round that to 1. Then 0.336 divided by 0.336 gives me 1. So far I have 1 mercury, 1 sulfur. So the only thing is figuring out the oxygen. So I go 1.35 divided by 0.336. I get 4.017. Again, it's close enough, just round it to the nearest whole. That should be about 4 oxygen. So the empirical formula for letter B should be Hg. 1, you don't have to write it down. So S, which is also 1, so I don't have to write it down. And O, I have 4 of them. So again, the empirical formula should be HgSO4. So let's look at an example of something that you'll see when it comes to a word problem and you're trying to find an empirical formula. Savannah is trying to determine the empirical formula of the compound from the percent composition of the compound that she was working with. I know that's pretty vague, but she's just working on secretive stuff, right? So help Savannah to figure out the empirical formula if she has 7.8% carbon and 92.2% chlorine. So I'm going to ask the teacher again to pause this video for maybe a quick 5 minutes or so and allow you guys to work on this with your partner. Good? So again, I'm just going to go through the steps without writing it down. I know that you only have two components to this compound, which is carbon and chlorine. So I'm going to turn that 7.8% carbon into 7.8 grams of carbon, and that 92.2% chlorine into 92.2 grams of chlorine. I need to turn that grams into moles, so I need to look for the mass of carbon, which is at 12.0. So I'm going to go 7.8 divided by 12, which gives me 0.65. Then I'm going to deal with the chlorine. I'm going to go 92.2 divided by the mass of chlorine, which is at 35.5, which gives me 2.597 or 2.6. So, or 2.60. So if I go pick the least amount of moles that I have, 0.65 moles compared to 2.60 moles. I know that 0.65 is the smallest, so I'm going to use that to be my denominator, or to divide both my moles by that. So 0.65 divided by 0.65 is 1. Then 2.6 divided by 0.65 gives me 4 exactly. So the empirical formula that you should have gotten is CCl4. So now we're going to move on to the last concept, which is how to find the molecular formula of a compound. So what is a molecular formula? So the molecular formula of a compound is either the same as its empirical formula, or it is a simple whole number multiple of that empirical formula. What do I mean by that? So the simplest one I can think of is H2O, right? So in that molecular formula, you have 2 hydrogen and 1 oxygen, H2O. So that's the simplest whole number ratio, or simplified whole number ratio that it can be, right? So that could be its empirical formula. So now for a molecular formula, you can have H4O2, right, which is a whole number multiple of its empirical formula, H2O. And again, it's kind of confusing, but I will show you an example, and hopefully it will be clear after you've watched this video. So here you go. So let's find the molecular formula of a compound. I'm going to do this by myself. Just follow along. Then I will give you some problems that you can work with. So here's the first one. It says right here, calculate the molecular formula of a compound whose molar mass is 60.0 grams per mole, and empirical formula is CH4N. So this is pretty vague. You know that you have 60.0 grams per mole of this molecular compound. The molecular compound composed of carbon, hydrogen, and nitrogen, CH4N. So the first thing that you need to do is find the empirical formula mass of the compound that you are working with. So the empirical formula mass is the same thing as finding the molar mass of the compound that you're working with. In this case, CH4N. So carbon is 12, hydrogen is 1 each, you have 4, so that's 4 grams, and nitrogen is 14.0, so 14.0 plus 4, that's 18, plus 12 in carbon gives you 30.0 grams. So the next step that you have to do is get the molar mass that you're given in the beginning, which is 60.0 grams per mole. Divide that by the empirical formula mass, in this case 30.0 grams. And when you divide 60 to 30, you get 2 moles. So that means that all I have to do is double all the element that I have in that empirical formula. So since I started with 1 carbon, 4 hydrogen, and 1 nitrogen, and in this case I have gotten 2, so that means I have to double everything. So instead of CH4N, it would be now C2H8N2. So I'm going to give you now a very complex question, something that you might see again on the quiz or on the test. So just bear along with me and go along, make sure that you're understanding this. So here is the practice problem. I'm going to go through it with you. It says right here, you find that 7.36 grams of a compound has decomposed to give you 6.93 grams of oxygen. The only other element in the compound is hydrogen. If the molar mass of the compound is 34.0 grams per mole, what is its molecular formula? So right now, it sounds complex, but it's actually not. So again, if you just go through it step by step, it should be doable. So the first thing is, again, try to find out what the question is asking you for. So what is the question asking you for? It's asking you for the molecular formula. Agree? For you to find the molecular formula, you know that you need multiple steps to get there. So we need to look at what you are given. So the first thing that you are given is that you have 7.36 grams of the whole compound. Out of that 7.36 grams, you know that you have 6.93 grams of oxygen. And the other component that is in that compound is hydrogen. So you know that you're only dealing with oxygen and hydrogen. So since you have the whole mass for the compound and you have a part mass of that compound, you should be able to find the mass of hydrogen. So how do I do that? Well, I know that I have 7.36 grams of the compound. 6.93 grams of that is oxygen. So that means that if I just subtract the two, I should get the mass of my hydrogen, which is in this case 0.43 grams of hydrogen. Good? So now the next step would be to find the percent composition of each of the components. So I need to find the percent composition of oxygen, then find the percent composition of the hydrogen. How do I do that? Well, we've been doing that. So I'm going to start with the mass of the component, in this case, the oxygen first. I'm going to go 6.93, right? Divide that by the mass of the whole compound, which is 7.36. I multiply that by 100%. That gives me the percent composition of oxygen. In this case, it's 94.2%. I can just subtract that 94.2% to 100%, and it'll give me the percentage of hydrogen. But if you want to be sure, then do the same thing that you did for oxygen. So I'm going to go 0.43 grams divided by 7.36 grams, which is the mass of the whole compound, times 100% gives you 5.8% hydrogen. So far, I know I have 94.2% oxygen and 5.8% hydrogen. I need to find my empirical formula so that I can find my molecular formula. For me to do that, I need to turn those percentages that I have and turn them into grams. So I'm going to start with turning that 94.2% into 94.2 grams. I need to turn that grams into moles, so I'm going to need a conversion factor. So I know that in 1 mole of oxygen, it weighs 16.0 grams. So I'm going to do my math and find out that in 94.2 grams, there's about 5.89 moles of oxygen. I'm also going to do this for my hydrogen. So I'm going to turn that 5.8% into 5.8 grams, multiply it by 1 mole, divide it by its molar mass, which is 1.0 grams. And in the end, you know that you get 5.8 moles of hydrogen. So again, I have 5.89 moles of oxygen and 5.8 moles of hydrogen. I'm going to take the least amount of mole that I have and divide that to all the products that I've gotten. So I'm going to divide 5.8 to the moles of hydrogen that I have and divide 5.8 to the moles of oxygen that I have. So in this case, when I go 5.89 divided by 5.8, I get 1.02. And when I divide 5.8 to 5.8, of course, you get 1, right? And instead of multiplying this to get rid of that 0.02, it's minuscule enough that I can just round it to the nearest whole. So I'm going to turn that 1.02 moles to 1 mole of oxygen and, of course, 1 mole of hydrogen. So now my empirical formula is OH, or 1 oxygen and 1 hydrogen in that compound. But you don't have to write that 1 as a subscript because it's assumed that if you put O, you have at least 1, and if you put H, you have at least 1. So the empirical formula is technically OH. But they're not asking for the empirical formula. Again, the question is asking for the molecular formula. So that means I have one extra step to do, which is what we've been doing, which is just looking at the total amount that you have. In this case, I have 34.0 grams per mole of the compound. Why is this important? Well, we need this to find your molecular formula. So that means that I need to find the empirical formula mass, since I've been provided with the molar mass of the compound already. So I need to look at my components. 1 oxygen, 1 hydrogen. 1 oxygen is 16.0 grams. 1 hydrogen is 1.0 grams. So my empirical formula mass is 17.0 grams. So what am I going to do with that? Well, we know that to find the molecular formula, we need to put the molar mass of what you're given and divide that to the empirical formula mass. So I'm going to do that right here. So 34.0 grams per mole divided by 17 grams. You know that you're left with 2 moles. So that means that I have to multiply that 2 to my empirical formula. So instead of O1H1, it would actually be O2H2. But the proper way to write that formula is H2O2. So I'm just going to correct it and put it that way. If you've left it at O2H2, then it is okay, because you probably did not know that H2O2 is the proper way to write down hydrogen peroxide. So again, O2H2 would be okay, but the better way to write it is H2O2. So hopefully you understood how to go from percent composition to empirical formula, and from empirical formula to molecular formula. So now you guys are going to work on the 10.3 section or chapter 10 worksheet practice problems that you guys have. Work on section 3, work as a partner, and next time we meet, you will get a quiz on section 3.